because of the infinite line charge, okay? And at the end of the day, you'll have to memorize the equation, final equation, okay? So that's like this, minus sigma r divided by 2 epsilon naught plus c. Once you differentiate this, okay, once you calculate negative gradient, this minus is going to cancel and differentiation of r is simply equal to 1 and differentiation of constant is equal to 0. So that it will become sigma divided by 2 epsilon 0, which is the electrostatic field due to the sheet, okay? The next is infinite line charge, okay? So for example, here we have infinite line charge. Its charge density is given, that is equal to plus lambda. This copy paste from Griffith, okay? Problem number 2.22, okay? On the 8th edition. Now here it is this plus lambda, and you are supposed to calculate what electrostatic potential at this free point. For example, here we have point P, which is at a distance of r from here, and you are supposed to calculate what is the electrostatic potential at this free point, okay? So we must know what is the electrostatic field at this point. Once we know the electrostatic field, then integrating that, we'll calculate the potential at that very point, right? And taking care of that, the electrostatic potential in this very problem will be non-zero at infinity. It will not be equal to 0 at the infinity. So infinity is not the reference point here as well, okay? So have a look, okay? Once we calculate electrostatic potential, then we'll discuss, then we'll have a discussion on this reference point, okay? So it's like this. First of all, what's the electrostatic field because of the line charge? Electrostatic field at this point will be in this direction, and how much is that? We have already calculated that using this Gauss law, that's equal to 2k lambda by r. 2k lambda divided by r multiplied by r cap. You can write it like this as well, multiplied by r cap, right? Where r cap is a unit vector that is directed radially outwards like this. This here r cap unit vector. This r cap unit vector, okay? So this is the electrostatic field because of this line charge plus lambda. Let me write down here electrostatic field. So electrostatic field due to the line charge is how much now? It's equal to 2k lambda, where k is electrostatic constant, which is in turn equal to 1 by 4 pi epsilon naught multiplied by r cap, fine? Now we can define the electrostatic potential by this equation. V at r, okay, as a function of r is equal to negative integral of E dot dr, okay? So again, here we'll define a reference point. For example, that reference point is something like this O, a reference point, okay, to r. From reference point to r, okay, we'll define the electrostatic potential at any point. Now, substituting the value here, this dr can be written like this. It can be written as dr multiplied by r cap. Then r cap dot r cap is equal to 1. So the electrostatic potential V as a function of r will be simply equal to minus 2k lambda first of all. Then integration of 1 by r into dr. Like this, it's integration of 1 by r, okay? And the limits of integration from a reference point to r, okay? Then what I will write down here is this potential at point r will be equal to minus 2k lambda multiplied by the integration of 1 by r is obviously equal to ln of r. So here I will write down ln of r, okay? And then whatever the limits of integration, that will be something like this, okay? So it's ln of r plus a constant of integration, that's called c, okay? Where the c is what? It is constant of integration, okay? So you can calculate the value of the c as well. For example, if you substitute the value of r equal to 0, then from there you can calculate the value of c is what? So it is that point where the potential is equal to 0, or it's the reference point, right? So this is the potential at any point. Now in case, suppose that you want to calculate the potential difference between 2 points. Suppose that here we have a line charge like this, okay? So this is the electrostatic potential. What this negative sign implies is this. Negative sign implies that potential, it implies this. Negative sign implies that the electrostatic potential, it decreases as r increases, okay? Okay, so I'll give an example here. Suppose that what I will do is this. Here is a point, and at this point a positively charged particle is placed like this, okay? Now it's released from this charged particle, from this point. Obviously its initial velocity is equal to 0. It will go from this point to this point, and at this point it will have some non-zero velocity, okay? Now it has some mass as well, so it is velocity, so it implies that it has absorbed some kinetic energy, which is equal to 1 by 2 mv square. Now the question arises, where its kinetic energy comes from? And the answer to the problem is that the kinetic energy comes from the potential energy, okay? Actually, when the particle goes from point A to point B, it goes from a region of high potential to a low potential, or from a region of high potential energy to a region of low potential energy. So that means the potential energy of the particle decreases, and which makes for what? The increase in the kinetic energy, okay? So the kinetic energy, it comes from the decrease in the potential energy. Okay, so from that, what's clear to you is this, that as you go from the point A to point B, the electrostatic potential of due to this line charge, that decreases. So that's what this negative sign implies here. That the electrostatic potential, it decreases, it dies down as the R increases. Fine. Okay, then you can plot this graph, and obviously this equation is this. You can plot the V. If, for example, the question is like this, plot plot V of R as a function of ln of R versus ln of R graph, like this, okay? Then what you can say is that it's a linear graph. It's directly proportional to ln of R. It's directly proportional to ln of R. So with a negative slope and positive intercept, so that means the graph will be something like this. So this here V of R as a function of ln of R, not as a function of R, but as a function of ln of R, okay? So it will be like this. It will be a straight line with the negative slope and positive intercept. It will be something like this, fine? Okay, where this is what? This is that, this is the intercept here, and this intercept here, this will be equal to C. It's equal to this, okay? So this is what? This is the value of ln of, this is the value of the potential where ln of R will be equal to 0, or when R is equal to 0, this is the potential, okay, which is equal to C, a constant, fine? And then from there you can calculate this as well. For example, if this is theta, so you can write down here this tan theta is in turn equal to minus 2k lambda, which is the coefficient of this ln of R. That's equal to minus 2k lambda. So this here tan theta, fine? So we have calculated the electrostatic potential because of this line charge. You can okay. So we'll calculate the potential difference as well, okay? So concentrate here, concentrate here. Suppose that the example is like this. Let me do a couple of examples on this concept. Okay, concentrate here. So example is like this. This is the example. Suppose that here we have this an infinitely large charged sheet, okay, whose charge density is uniform and which is in turn equal to plus sigma. Fine. Now here we have one point is point A, and this another point, that's point B. Fine. Okay, the question is like this: calculate. Now there's the charge particle Q, whose charge is Q and its mass M, and it's at rest. This charge particle is at rest. Now obviously because of the force of repulsion, this charge particle will go from A to B, isn't it? Its initial velocity is 0, so velocity here that's equal to 0. Then at this point it will have some non-zero velocity. V is equal to what you are supposed to calculate it, okay? So what we have to calculate is this. Calculate A part, potential difference between A and B. Potential difference between A and B. Number one, you are supposed to calculate this, the potential difference between the points A and B. And number B is that you will have to calculate what's the velocity of the particle at the point B. You have to calculate what is the velocity of the particle at point B, okay? So concentrate here. So let me first of all calculate the potential difference, okay? So potential at the point A will be obviously equal, that's equal to, field is equal to sigma by 2 epsilon 0, okay? Then multiplied by R with the negative sign, so that if we'll differentiate it, if we'll take its negative differentiation, it will become sigma by 2 epsilon 0, which is the electrostatic field, right? Plus a constant of integration that will be equal to C. And this here are, for example, these two distances are given to you. The distance from here to here, this mentioned this equal to R. From here to here, the distance equal to R. And then again from A to B, that's also equal to R. So that means the separation of the point A from the sheet is equal to R. And the separation of the point B from the sheet, that's equal to R plus R, which is equal to twice R. Fine? Okay, so the potential of the point A will be obviously equal to this because the distances are. Then the potential at the point B will be equal to something like this, minus sigma divided by 2 epsilon 0 multiplied by, here I am going to write it 2R plus constant of integration, which is C. Fine? Okay, with the potential on the sheet. Okay, when R is equal to 0, so C will be equal to potential at R equal to 0. Fine? Okay. Then what I will do is this. Now obviously the potential at the point A is greater compared to the potential at point B. So let me calculate the difference of the two. So what I will do is this. I will try to calculate VA minus VB. VA minus VB. So it will be in turn equal like this. This C and C is going to cancel. This will become positive. This will be a negative minus sigma multiplied by R by 2 epsilon naught. And then here it will become positive. This will be here sigma R by epsilon naught. 2 and 2 is going to cancel. Sigma R by epsilon naught. Now it's like this, minus 1 by 2 plus 1, that's equal to 1 by 2. So it will be in turn equal to sigma into R divided by 2 epsilon naught. So that means what is the potential difference between the points A and B? That's equal to what? The potential difference between the points A and B is equal to this. So here I will write down delta V, the potential difference, or it's equal to VA minus VB, which is in turn equal to what? That's equal to sigma into R divided by 2 epsilon naught. Okay, this is the potential difference. We are done with the part A. The part B is that we have to calculate. Suppose that a charge particle is it's released from the point A. Now it's at rest. It implies that it is velocity is equal to 0. Then because of the force of repulsion because of due to the sheet, okay, the sheet being a positively charged sheet, it will exert a force of repulsion on the particle A. So this particle A, it will get accelerated in this direction, okay, and the force will be a non-uniform force, isn't it? The force will be variable force as the particle goes from A to B. Okay, so from there what you can say is this, rather this will be a, no, it will be a constant force. Okay, so there are two ways you can calculate this velocity at the point B. Because the electrostatic field, because of this, is uniform. If the electrostatic field because of this uniform, that's not a function of R, then the force force on the charged particle will be also constant. When the force on the charged particle is constant, it in turn implies that the acceleration of the charged particle will be uniform. And when the acceleration of the charged particle will be uniform, that means you can apply the equation of motion between the point A and B, and from there you can calculate what is the velocity of the particle at point B. Okay. Now, for example, there is line charge. Now you know that because the line charge, the electrostatic field, that's not constant. That is function that varies as r. So when the electrostatic field is not constant, it implies that the acceleration is not constant. When acceleration is not constant, so you cannot use the equation of motion. But what you can use is that you can use the energy conservation. Okay, energy conservation is always true. The only constant for the energy conservation is that the forces must be conservative in nature. And here, obviously, electrostatic force between this sheet and this charged particle is obviously conservative. That's electrostatic, which is conservative force. So you can safely apply both the equation of motion in this very example as well as the energy conservation. But if, for example, it's line charge, then in that very case you cannot apply what? You cannot apply the equation of motion. Rather, you will have to apply the energy conservation. But energy conservation is that is the easier way to do it. So what I will do is this. So you concentrate here. I will write down simply that the total mechanical energy of the particle at point A will be equal to total mechanical energy of the particle at point B. But the mechanical energy is in turn equal to kinetic energy at A plus potential energy at A is equal to kinetic energy at B plus potential energy at the point B. Fine. Okay. Which means that now we know that the potential energy is in turn equal to charge multiplied by electrostatic potential at point A is equal to kinetic energy at B plus charge multiplied by electrostatic potential at point B. Fine. Okay. So let me work it out. So you concentrate here. Okay, अच्छी तरह से ध्यान रखना बेटा. So concentrate here. So what I will do is this. Now here I will write down the kinetic energy at point A plus charge multiplied by potential at point A, which is the potential energy of the charged particle at point A, is equal to kinetic energy of the particle at point B plus Q multiplied by potential at the point B. Fine. Now this is equal to 0 because the charged particle starts from rest. This here equal to Q multiplied by potential at A is how much? That's equal to minus sigma into R divided by 2 epsilon naught plus constant of integration. Okay, you can avoid this constant of integration because anyway that is going to cancel. Then here kinetic energy at the point B will be obviously equal to 1 by 2 m into v square. We are supposed to calculate this v here. Then here it will be equal to plus Q multiplied by this minus sigma into, so here I will write it down. Wait a second. Let me write it down here. So here I will write down plus. Let me write down here plus. Then here it is Q multiplied by minus sigma into 2r, because the separation of the point B from the charged sheet is 2r divided by 2 times epsilon naught, then multiplied by, then here it is plus constant of integration c. Fine. Okay. So then next what I can write is this. Next what I can write is this. This constant of integration is going to cancel with the constant of integration. Rather it is here. Square bracket is here. This square bracket is somewhere here. Wait a moment. This constant of integration, this rather QC and QC, it is going to cancel anyway. Then here what I will write down is this. It will be equal to here sigma multiplied by r divided by epsilon naught. This negative, it will become positive here. Then here it is minus q times rather. Then here it is minus q times sigma multiplied by r divided by 2 epsilon naught. Then on the RHS what we have is this 1 by 2 m into v square. Then this is 1 minus 1 by 2. Obviously that is called 1 by 2. So what I will write down is this q multiplied by sigma into r divided by 2 into epsilon naught. That will be in turn equal to 1 by 2 m into v square. Then from there I can calculate the velocity of the particle. This 2 and 2 is going to cancel. So velocity v will be equal to q into sigma into r divided by m multiplied by epsilon naught root of this. This is the velocity of the charged particle. Right? Okay, this is the velocity of the charged particle. Okay, there's one more alternate way as well. Okay, so here I will write down alternate method. Okay, so the alternate method for this problem is like this. We can apply the equation of motion. The reason is this. We can apply equation of motion. Why we can apply the equation of motion? The reason is that the electrostatic field due to the point charge is what? That is constant. Okay, then I can write down this equation that v square minus u square is equal to 2as. This is the equation of motion. Okay, then v square के बदले में क्या लिखूं बेटा? So v square I have to calculate. U square is equal to 0. So here I will write down 0. This equal to 2, and this acceleration is obviously equal to what? That's called force per unit mass. So here I will write down force by mass. Then multiplied with the separate distance covered by the charged particle. You see what the distance covered by the charged particle, that's called r. Initial separation from this r and final separation is r, 2r, sorry. So the distance covered by the charged particle is obviously equal to r. So s के बदले में क्या लिखूं बेटा? So s will be replaced by r, like this. S will be replaced by r. Then here it is V square is equal to 2 multiplied by, this will be replaced by Q into E, because force on the charge particle is charge multiplied by electrostatic field divided by mass multiplied by R. Then we can also write it like this: 2 multiplied by Q divided by M multiplied with this. E will be replaced by what? It is electrostatic field due to the charged sheet is equal to sigma by 2 epsilon 0. 2 epsilon 0 then multiplied by R. Okay, fine. The next what I can do is this. Concentrate here. So what I will do is this. So velocity V will finally equal this. 2 and 2 is going to cancel. So velocity V will be equal to under root of what? Under root of all this, which is called Q sigma R divided by M epsilon naught. Q sigma R divided by M epsilon naught. Okay. So the answer will be exactly same, isn't it? Answer here and here will be exactly same. I can use the equation of motion. The reason is that electrostatic field is constant. Okay. Oblique force is constant. Oblique acceleration is constant. And we know that the equation of motion can be applied only if the acceleration is constant. They are true only for uniformly accelerated motion. Otherwise not. Fine. But the equation of this energy conservation, it is true in general. Suppose that we have a line charge in R, for example, there is a charged sphere. You know that the electrostatic potential due to the charged sphere is not constant. That is function of R. In such a situation, you can never apply the equation of motion. Okay. But what you can do is this: you will apply the energy conservation. Okay. And energy conservation is always handy to use. The reason is that it does not involve any integration, any sort of integration, any sort of differentiation. It is simply like what energy conservation is simply like what 2 plus 2 is 4. It's like that. Okay. Simply you will have to equate the mechanical energy on the either side, and then try to work out that and try to calculate what's the unknown parameter. Fine. Okay. Let's do the another example like this. Or rather, I will keep this as information for you. This is another example, example number 2. That is based on the same concept. It's something like this. This is a line charge here. Its charge density is plus lambda. Then here we have this our point A and this point B. Fine. Point A is at a distance of R from this line charge. Okay, let's suppose this is equal to R. And the separation between the point A and B, let me suppose that it's equal to R. So that means the separation of the R, separation of the point A from the line charge is equal to R, and the separation of the point B from the line charge, that's equal to 3R. Okay. In this very case, you can never apply what? You cannot apply this equation of motion. Why? What's the reason? The reason is this: electrostatic field due to the line charge is equal to 2k lambda divided by R. Now it is a function of R, isn't it? When it's a function of R, so that means it's not constant. Okay, as the charge particle, this charge particle Q, whose mass equal to M, as it goes from A to B, as it gets accelerated from A to B, the force of the charge particle is not going to stay constant, which implies the acceleration of the charge particle is obviously not constant. Okay, that's variable acceleration. When that's variable acceleration, we cannot apply the equation of motion. But what we can do is that we can apply the energy conservation. Mechanical energy at the point A must be equal to mechanical energy at the point B, because the criteria for the mechanical energy conservation is that the force must be conservative in nature. And obviously here the force is conservative in nature, which is electrostatic force, and that's indeed conservative in nature. Fine. So this will stay as a home assignment for you. Number first is that A parts like this. So let me write down the question here. You just wait a moment. So here I'm going to write down the question. So calculate. A part is that you will have to calculate the potential difference between the points A and B. That means VA minus VB. You will have to calculate. And B part is that you will have to calculate what is the velocity of the charge particle when it reaches point B. Okay, you will have to calculate that as well. Right? So I'm sure you can do both these examples. Example number 1 as well as example number 2. Okay. Ab dekh lo beta. There's another question that's like this: electrostatic potential due to the line charge lambda at a distance R is what? It is asked in net December 2018. So what is the electrostatic potential? That's simply like this. What you can write is this: V as a function of R is equal to this. If you know the electrostatic field, you know, for example, know what is the electrostatic field. Suppose that you don't know the potential, okay, but you know the electrostatic field, that's equal to 2k lambda divided by R. Okay. Now integrate it. So you know that the integration of 1 by R is called ln of R. So it will be something like this: minus 2k lambda is a constant which will stay as side into ln of R plus a constant of integration C. That's it. This is the answer to the problem. Okay, so we are done with the problem. Right? And this has been asked as such in the December 2008. Okay. The next it's like this: charged hollow sphere. Okay, so it's like this. This is a charged hollow sphere, or it can be a solid sphere but conducting. In both the situations, if you give charge to the sphere, the charge will reside only on the surface. In detail, we have discussed that already. Okay, why the charge particle is reside only on the surface? The force of repulsion is not the reason, but what's the reason is the electrostatic potential energy. We are yet to discuss the electrostatic potential energy. Fine, and there are a good number of questions which have been asked in the electrostatic potential energy in the previous years. Okay, so let me concentrate on this: the charged hollow sphere. Okay, so it's like this: a charged hollow sphere. It's a charged hollow sphere. Fine. Now the charge is given to it, so the charge will obviously reside only on the surface. And the charge is given to it, it's going to reside on the surface. The reason is that inside there's no meat, when there's no matter, so how can charge reside? Okay. Okay, so this here charge, and then its radius is equal to capital R. This follows it here. We are supposed to calculate the electrostatic potential both inside as well as outside. Okay. So what is the procedure? The procedure is this: you can calculate electrostatic potential only if you know the field. Fine. Okay. Now I will show here a technique. Okay. So number one is that you can memorize what the electrostatic potential inside and what the electrostatic potential outside. Number one is that, and number second is that you can derive it out as well. Okay. And for the competitive exams, you have to memorize the result. Okay. Now why I will show it to you. The reason is that, for example, there is solid second, and suppose the solid second is non-uniform. Then in that very case, you will have to calculate the electrostatic potential by solving the integral. So you must be knowing how to solve the integral. Okay. And you cannot expect a direct question from the hollow sphere, calculate electrostatic potential in the hollow sphere, or calculate the electrostatic potential to the uniform solid sphere. But you can expect a question like this: there is a solid sphere which is non-conducting, whose charge density is function of R. It's something like rho is equal to K multiplied by R. Then you are supposed to calculate the electrostatic potential difference between 2 points. You can expect such a question that is asked in the net examination or the just examination or gate examination, whatever. Fine. Okay. So that means you must be able to solve the integral. Okay. You must know the technique how to do it. Okay. How to calculate the electrostatic potential at any particular point. Fine. Okay. Now, in order to calculate what electrostatic potential, you must know what's the electrostatic field, the hollow sphere, and you know that. Okay, I expect you know that electrostatic potential field inside will be equal to 0. So that means when small r is less than capital R, and outside it's equal to K multiplied by Q divided by R, where K is electrostatic constant, R is radial distance, Q is the charge on the surface. And this is true when small r is greater than capital R. So this is the electrostatic field. Okay. Now we know the electrostatic field. So when we know the electrostatic field, so we have to calculate what electrostatic potential. Okay. So let me calculate first of all electrostatic potential outside. So here I will write on KQ by R square. Sorry, it's here KQ by R square. The field is KQ by R square. Okay. So let's calculate what first of all what electrostatic potential outside. So here I will write down outside. Okay. So outside implies that small r is greater than capital R, and here we assume that the electrostatic potential becomes 0 at infinity. Okay. Later on we'll calculate the electrostatic potential. Electrostatic potential outside becomes equal to this, that is V is equal to K multiplied by Q divided by small r. This is the electrostatic potential because of this. Now obviously V is inversely proportional R. That means when R is equal to infinity, potential will be equal to 0. Okay, which implies that the infinity is the reference point here in this very case for the hollow sphere, not for the line charge, not for the surface charge, but for this infinity is indeed the reference point. Fine. Okay. So how to calculate it? So what I will do is this: we have the electrostatic field, so I have to calculate the electrostatic potential outside. So simply what I will do is this: I will write down this integral V of R is equal to minus times integration of E dot dr. E dot dr like this. Fine. Okay. From infinity to point R. From infinity to point R. Okay. Now what is the electrostatic field outside? Electrostatic field outside is obviously equal to this. So let's substitute here. So this will be V of R is equal to more what this E dot dr will be obviously equal to what E dr multiplied by cos 0, and cos 0 is equal to 1. So then this KQ is a constant, so it will be equal to minus times KQ into integration of R is to the power minus 2 with respect to R, and the limits of integration will be going from infinity to point R. Okay. Then on solving this integral, you can safely solve this integral. It will be R is power minus 1 divided by minus 1. This negative sign is going to cancel, and here it will be equal to 1 by R. Then apply the limits of integration. This lower limit is going to vanish because 1 by infinity will be equal to 0. So finally the potential at point R will be equal to K Q divided by R. That's it. This is the electrostatic potential, and this is true when small r is greater than capital R. That means it's the electrostatic potential outside. So this is the electrostatic potential outside. Moreover, if you will calculate its negative differentiation, okay, negative gradient, the differentiation of 1 by R is obviously equal to 1 by R square minus times 1 by R square. Negative sign will absorb, so that means the electrostatic field will be obviously equal to KQ divided by R square. Okay. Then let's calculate the potential. So B part is that let's calculate the electrostatic potential inside. Let's calculate the electrostatic potential inside. अब यहाँ ध्यान रखेंगे बेटा आप. Okay. So let's calculate the electrostatic potential inside. Inside implies that somewhere, outside implies that somewhere here you are supposed to calculate. So this one point which is point P, and at point P you will have to calculate the electrostatic potential. Okay. So we are done with this. Okay. So physically what actually we have done is this: we have taken a test charge whose charge is equal to 1 coulomb from infinity to this point, and then we have calculated what is the work done by me. Okay. Then the work done by me will be stored as the electrostatic potential energy of the point P of the charge particle, sorry, which is the test charge, which is equal to 1 coulomb. Okay. So that's how we define the electrostatic potential at the point P. Okay, this integral it invisibly means that's what we are doing. So this actually what the work done in taking a charged particle whose charge is equal to 1 coulomb from infinity to that point, which is point R. Okay, which is point P, and whose radial distances are to the center. Fine. Now we have to calculate the electrostatic potential somewhere here at this period point. Suppose that this point is PQ. Let it be point S. We have to calculate electrostatic potential at point S. So this R is less than capital R. Fine. As will अब आप यहाँ ध्यान रखोगे बेटा. As I will take the charge particle from infinity to the point S, okay, the electrostatic field behavior is not going to remain same. In this very case, as the charge particle is taken from infinity to point P, the electrostatic field that varies indeed, but the behavior remains unchanged. That means the electrostatic field will be always proportional 1 divided by R. But as you take the charge particle from here to here, from infinity to point S along any path, okay, when the charge particle is taken from 1 coulomb is taken from the infinity to the surface, the electrostatic field varies as 1 by R. And when it is taken from the surface to the point S, the electrostatic field inside that, you know that that's equal to 0, isn't it? So accordingly, I will break the integral. This is what I will write. So I will write like this: electrostatic potential at point R will be equal to simply the same integral here minus infinity to point R E dot dr. Okay. But what about this electrostatic field? Okay. Should I substitute the value of E as 0, or should I substitute the value of E as kq divided by R square? Okay. So it will depend. It will depend, because the reason is that as the charge particle is taken in this very case from infinity to point R, in that very case the electrostatic field is not, its behavior does not remain constant. What is electrostatic field actually is this, that the electrostatic field is equal to kq divided by R square, and it is true when small r is greater than capital R, and then the electrostatic field suddenly becomes equal to 0 just when you enter this this hollow sphere. It becomes equal to 0. This is true when small r is less than capital R. So accordingly, what I will do is this: I will have to break this integral. Fine. Okay. तो आप यहाँ ध्यान रखेंगे बेटा. Okay. So what I will do is this, and this is a mathematical step, and I'm sure आपने ये mathematical step calculus में already पढ़ा होगा. Okay. So you concentrate on this. Okay. So what I will do is this: I will write down the electrostatic potential at point R. I have to calculate. I will write down this integration from infinity to point R to point capital R, which is the surface. Okay. Then electrostatic field. So this is the electrostatic field outside, dr, something like this. Fine. Okay, then minus here, so rather it's actually plus here. Okay, plus integration from capital R to small r, this inside. Okay, as you are moving from infinity to the point S, the electrostatic field outside and inside, that's not same. Okay, the behavior is entirely different. So something like this it is. Wait a second. Okay, it's something like this. This is the integral we are going to solve. Fine. So here it's negative sign. Okay. Now, what is the electrostatic field outside? That is equal to kq by R. So kq by R square. So here I will replace it by kq by R square. So V of R is equal to this here negative sign minus. Then here it is kq divided by R square. Kq divided by R square dr, and the limits of integration will be from infinity to capital R. And this here minus plus is minus, and this integral is going to vanish. Why? The reason is that electrostatic field inside is equal to 0. So when it's equal to 0, so obviously this integral is going to vanish. Okay. Then here we have. Now its integration of 1 by R square will be obviously equal to minus 1 by R. This negative sign will vanish here. Okay. Then kq will, it's a constant, it will stay as such. Then you apply the limits of integration, it will be something like this. Okay. So here finally the potential at the point R, which is less than capital R, will be something like this. It will be equal to kq by capital R. It will be equal to kq divided by capital R. Okay. So this is here, its integration will be minus 1 by R. Negative sign will cancel. Then it's 1 by capital R minus 1 by infinity. 1 by infinity is going to become 0. Then it's kq divided by capital R. Now obviously it's obvious that this kq divided by capital R is a constant, isn't it? It's not a function of R. So obviously the electro potential inside that's equal to constant. ठीक है ना बेटा? Okay. Now let's have a bit of discussion on this. अच्छी तरह से यहाँ ध्यान रखना बेटा. So suppose that here we have a hollow sphere which is charged. It's like this. It's something like this. Now you know the electrostatic field here. Electrostatic field here that is equal to kq divided by R square. And electrostatic field inside will be equal to 0, isn't it? Now, if the electrostatic field inside is equal to 0, it does not necessarily mean the potential is equal to 0, okay? Because if you differentiate, for example, 0, it will become 0. But if you differentiate a constant, it will also become 0. So there are two possibilities. Possibility number 1 is that the potential will be equal to 0. And the possibility number 2 is the potential can be constant as well. And what we have arrived at is this, that the electrostatic potential inside that is constant and not equal to 0, that is constant. So what is the potential outside? That is called kq divided by R. And what about the potential inside? That's equal to kq by capital R. Okay, kq divided by capital R. So that means the potential in the center at the surface is same, which is called KQ divided by capital R. Then outside it dies down as 1 by R. So outside it will be a rectangular hyperbolic graph. Okay. So I'm sure आपको यहाँ तक अच्छी तरह से समझ में आया होगा how we have calculated potential both inside as well as outside. We are well acquainted with the field now. Here we have calculated potential as well. So let me plot the graph here. Okay. So let's plot the graph here. One will plot the graph E versus R, and number next is that we'll plot a simultaneous graph of E as well as B. Okay. There's a possibility that such a question can be asked in the competitive exams. अच्छी तरह से यहाँ ध्यान रखना बेटा. Okay. So what I'm going to do is this: plot V as a function of R versus R graph. Okay, you are supposed to plot this graph. Fine. So safely you can plot. Inside the potential is constant, and outside it dies down as 1 by R. So that means the graph will be something like this. So this will be here V as a function of R, and then here it is R. Okay, so this here capital R. Okay, surface. Now inside the field is the potential is constant, so it's like this. Inside the potential is constant. If you find the slope of this, the slope will be equal to 0, and you know that the negative slope of the potential will be equal to the field, and hence field is equal to 0, and then it will die down as 1 by R. So it will be something like this. So here it's V is proportional to 1 divided by R, and here V is equal to constant. Fine. And here the potential that's equal to what? That's equal to KQ divided by capital R. This is the potential like this, and here it's KQ divided by small. Dies down like this. Okay. Then you can do one more example here as well. You can do one more example, and that's like this. Okay, you can do this example as a plot E and V versus R graph. You know for what? For you know that for hollow sphere. So here I will write out for hollow sphere, for edges. That means hollow sphere. Okay, so it will be something like this. So this here, for example, E and V, electrostatic field and potential versus R graph. So first of all, we can plot the field graph. So what will be the field graph? Okay, so this here capital R. Wait a second. This here capital R is the surface. Then the electrostatic field graph will be something like this. It will be something like this. This will be the electrostatic field graph. Then like this. Fine. And what about the potential graph? The potential graph will be obviously like this. It will be something like this. Inside it is a constant. Then outside it is proportional 1 divided by R. That means the slope will be lesser. The steepness will be lesser. Okay, so this is the potential graph and this is the field graph. Okay, this is the field graph. You know what for hollow sphere. Okay, I'm sure this is now clear to you. Okay, now next let's move to another example, and that is like this. Copy paste from David Griffith, problem number 2.21 on the addition number 8. Okay, then it's a charged solid sphere. Okay, and we are supposed to calculate the electrostatic potential both inside as well as outside. Let me keep this as home assignment for you, and I'm sure that you must be able to calculate it. Okay, so first of all, I will write down the electrostatic field. You know that the electrostatic field outside that is equal to KQ divided by R square, and inside that is that's what. And so this is true when small r is greater than capital R, and inside the electrostatic field is non-zero, which is called KQ multiplied with small r divided by capital R cube. Take care of dimensional consistency. This is true when small r is less than capital R, and electrostatic field being proportional to R. Right? In this very case, you can calculate the potential both inside as well as outside. Okay, and then compare the two potentials. What is the potential at the surface? What is the potential at the center, and so on. Okay, so I'm sure you must be able to do this. Okay. So next, हमारे पास एक example है बेटा, that is net December 20. That has been asked in the net December 2016. Okay. So first of all, I will write down what is the potential here. So let me write down the potential here. This will stay as a home assignment, but first let me write down at the end what's the answer to this problem. Okay, then accordingly we will do it. So wait a second. So here when you will calculate the potential, it will be something like this. Potential outside will be equal to KQ divided by small r. This is true when small r is greater than capital R. Fine. Then potential inside, V as a function of R. Inside it is something like this. KQ divided by 2 multiplied by R cube multiplied by 3 into R square capital R square minus small r square. This is true when small r is less than capital R. Then from here you can calculate what the potential at the center point. So VC, center implies that small r is equal to 0. So it will be obviously equal to 3 divided by 2 multiplied by KQ divided by capital R. Isn't it? When small r is equal to 0, this term will vanish. This r square will cancel with r cube. So we are left with only this r. So it is 3 by 2. And what's the potential at the surface? At surface, it implies small r is equal to capital R. So 3r square minus r square will be equal to 2r square. 2 and 2 is going to cancel. So potential on the surface will be equal to k q divided by capital R. And obviously the potential at the center is greater than the potential at the surface. Okay. And that too I can write like this. Vc is equal to 3 by 2 times or 1.5 times. I can write like this as well. The potential at the surface. Like this I can write it. Okay. Okay, so you'll have to do this. Okay, you'll have to evaluate it. How to evaluate it? First of all, you know the field outside that is called kq divided by r square. Then exactly in the same as we have already done in case of hollow sphere, the potential will be exactly same. Exactly by the same procedure, it will be called kq divided by r. Then potential inside you have to calculate. Break the integral from infinity to capital R and from capital R to small r, but the field inside that's not equal to 0. Then accordingly we calculate it, you will arrive at this very equation. I'm sure you must be able to do it. So there's no rocket science in it. Sums are integral hand, so you can solve that out. Okay. Then the potential at the center is this, and the potential at the surface is this, which implies that as you move from center to surface, the potential dies down, it decreases down. Okay. Potential center is maximum, and then accordingly plot the graph yourself. Okay. So that will stay as a home lesson for you. We'll do this example which has been asked in the NET December 2016. Let me first of all make a diagram here. Okay. Then accordingly you can calculate what's the potential difference between the 2 points. Okay, let me first of all make a diagram here. And this question has been asked in NET December 2016. The question is like this. Here we have this is one sphere, and this diagram is given to you. Okay, then this is another sphere. They are just touching each other like this. The two non-conducting spheres. Fine. Its charge is given to it's equal to plus q. Its charge is given minus q. Okay, but the charge resides inside as well. Okay, so they are non-conducting solid spheres having the same charge. Fine. And the radii of 2 is given to you. Radius of this is given, it's equal to a, and radius of this sphere is also given to you, that's also equal to a. They are identical spheres having same charge. Okay. Now there are 2 points. Here it is point A and here it is point B. Here it is point A and point B. You will have to calculate what potential difference between points A and mine. So potential difference between A and B. Okay, question is like this. Calculate potential difference between points A and B in the figure. Okay, asked it in NET December 2016. Not a big problem. Okay, so you must be knowing what is the potential inside and on the surface and all that. Then from there you can calculate safely. Okay, so you concentrate on this. We'll be doing this last example here. Wait a moment. Okay, so first of all, let me write down what the potential at the point A. Okay, so what will be the potential at point A? We're left with 1 minute, I think. I think I will stop here. Okay, let me show you this example tomorrow, but this example will stay home lesson for you. Okay, so if you have any questions you can WhatsApp me. Okay, beta. So I'm sure आज मैं थोड़ी सी speed fast रखी है बेटा. Okay, so I'm sure you are able to follow me. Okay, so you take care of yourself. So ये question हम कल कर लेंगे बेटा.